Hello everyone. In the last class, we have started discussion on the gamma ray logging tool, and we were discussing about its application and the different factors which can affect the tool log responses. Today we will continue on the discussion on our gamma ray logging tool. So these are the topic that we will cover today. The tool performance, that means different factors which can affect the tool log response, and what are the precautions and things that we need to keep in mind before running the logging tool inside the wellbore. And then we will discuss quantitative application of gamma ray log. One of the parameters that you need to keep in mind while running the logging tool is its logging speed and the time constant. Logging speed and time constant must be optimized to get a very good gamma ray log record, which is representative of the true gamma ray radiation coming from the formation. For example, statistical variation can exist in the gamma ray log record. It happens because of two things. First thing, that is the how much gamma ray coming from the formation is not constant. That means the number of gamma ray which is emitted by the formation may vary with time to time. And second thing, what type of tool you are using and how much incoming gamma ray it is going to count per second. For example, if a tool is there inside the wellbore and 100 gamma ray is coming from the formation, the tool may not be able to detect all of the gamma ray every time. Sometimes it may record, let's say, 98 gamma ray per second, sometimes let's say 97. And when it is coupled with the natural gamma ray radioactivity of the formation, which is not constant, that means at every second or at different time interval, the formation may not emit the same amount of gamma ray. So because of that, statistical fluctuation in the gamma ray log record will exist. So if you run the gamma ray logging tool in a wellbore at two different times, you are not going to reproduce the same type of gamma ray log record every time. This will not happen in case of other logs such as resistive log. So if you use a same electrical logging tool to measure the formation conductivity or the resistivity of the formation, every time you are going to almost get the same resistivity or conductivity, provided the tool is same and the borehole environment is same. But in the gamma ray log record, some statistical fluctuation will exist. So these must be minimized to get a good idea about the actual gamma ray radioactivity of the formation. For example, its fluctuation may be in order of 2 to 10 API in gamma ray log record. You may think that this fluctuation is very small, but in zones where the gamma ray log record supposed to have low gamma ray count, where the gamma ray radioactivity is very low, this will hinder in the detection of those bits. So we must find a way to minimize these statistical fluctuations. We know that the tools are run inside the wellbore, and whenever we take the logging record, it is taken when the tool is running condition. The tool is never stationary for most of the logging tool, and always the record is taken when the tool is moving. So in that case, two things can happen. Either the tool is moving very fast or the tool is moving very slow. For example, if you see in this figure, in the first case, the velocity of the tool is 600 feet per hour, and third case, the velocity of tool is 5400 feet per hour. As I mentioned that the number of gamma ray coming in the formation may vary little bit with time to time. So if my tool velocity is very fast, what will happen is that I am giving less time to the tool to investigate the formation. So what is my objective? My objective is to get the gamma ray count per second. So let's say if I keep the tool stationary at a particular depth and I let the tool record the data for, let's say, 1 minute, and then I average the count rate for per second, so I will get a very good record because the tool is looking into the formation for 1 minute and it is getting a large amount of data, and then I am averaging it, so I will get an average count rate per second which will be very good and can indicate the true gamma ray radioactivity coming from the formation. But let's say I'm only giving the tool, let's say 1 second time to take the record from the formation. This way what will happen is that the tool is getting very less time. So the tool is taking very less time to get the record from the formation. Some fluctuation will vary. So if I keep the tool at a particular depth and I record the data in 1 second interval many times, every time I am going to get a different count rate. So here the advantage of averaging is lost. In the first case, when the tool was taking the record for every 1 minute, I am getting an average data which was representative of the true gamma ray radioactivity of the formation. So that means if my tool is moving very fast, I am not going to get the benefit of averaging of the data at a particular depth, and I will have less repetitive data of the formation. So in this figure you can see when the tool was moving slow, this is what we are getting. We are getting a constant values across the sand formation. But you can see in this synthetic log, when the velocity is around 1800 feet per hour and when the velocity is further increased to 5400 feet per hour, we can see we are getting a bad record. That means we should keep the tool velocity low in order to get a very good record. But is it possible to keep the tool velocity very low? It will result in very long wireline logging operation hours. So when you are doing the logging, well is stationary. That means no drilling is being carried out. Generally, we take the open hole logging record after drilling every section of the well bore. So you want to start the drilling as soon as possible so that you can minimize your drilling cost. So we cannot keep the tool velocity very low. But if you keep the tool velocity very low, we are going to get a good record. If we keep the tool velocity very high, we have seen here, we are not getting good record. In fact, tool response is, you can see it is shifted along with the movement of tool. So here this is the actual record, and you can see at high velocity this record is shifted here. This peak or this value of the gamma ray count across the sand I am getting somewhere here. So these things can be optimized by having a logging speed and a time constant. A time constant is nothing but it's a time over which the data taken by the logging tool is averaged. Generally, the critical thickness of the bed in order to be detected can be defined as velocity multiplied by the time constant of the tool. If a bed thickness h is less than hc, it may not be detected at all, or the record taken against that formation will not be as accurate as the true natural gamma ray count coming from the formation. Generally, value of SC we take 1 to avoid excessive distortion of the gamma ray curve. This could be better understood by this example. For example, in a logging tool, if I take let's say 9 times per foot, that means over 1 feet interval of the formation, how many record I'm going to take? I'm going to take 9 record. And how much time I'm going to spend? 1 by 3 seconds. That means let's say I'm going to take 9 record. That means every 1 by 9 feet interval I'm going to take 1 record. This is 1, 2, 3, 4, 5, 6, 7, 8 and 9. 1, 2, 3, 4, 5, 6, 7, 8 and 9. And every 1 by 9 foot I'm spending how much time? 1 by 3 seconds. That means to take a record from 1 by 9 feet interval of the formation, I am spending 1 by 3 seconds per record. Now you can see these are the 9 intervals: 1, 2, 3, 4, 5, 6, 7, 8 and 9. And these are the gamma ray count recorded from each record. So to summarize, the tool was taking 9 record in every 1 feet interval of the formation by spending how much time? 1 by 3 seconds. So these are the count rates when the time constant is 0.33 second or 1 by 3 second. That means the data is going to average every 1 by 3 seconds. So the time spent per record is same as the time constant, so there will be no averaging done. So you can see the first interval, the count rate per second will be 12 count rate per second. So you can see now in 1 feet interval of the formation, the count rate is varying from 9 to 18, and this 1 feet of formation is belong to the same formation interval. So in same formation interval, I am getting record from as low of 9 to 18, somewhere 9 and somewhere double the 9, that is 18. And it is not possible that same formation will have different gamma ray radioactivity. So there is statistical fluctuation exists in this formation interval. So this could not be eliminated by having a time constant of 0.33 second. If I take a time constant of 1 second, that means every 1 second I'm going to time average the data. So you can see every 1 second, that means the first three interval, this, this and this, I'm going to average the data. So that average data is how much? 14. So mean count rate per second is 14 count rate per second. This 14 count rate per second is nothing but record against what? 9 times per foot. So 1 by 9 into 3 or 1 by 3 feet. So 14 gamma ray count per second against 1 by 3 feet of the formation. So I will have now 3 interval only. In second interval, simply if I average, I will get 12, and third interval I will get 13. Now you can see the fluctuation is minimized. I have the mean count rate from 12 to 14 only. If I take a time constant of 3 seconds, that means I am taking 3 seconds for 1 feet, that means whole count rate for 1 feet. What is the whole count rate? That is 39, or the mean count rate will be per second 39 by 3, that is 13 feet per second. So this is a single record again 1 feet of the formation. So if I plot all the record in all the time constant, it will look like something this. So let's say this is my depth. When the time constant was 1 by 3, I will have record something like this, some fluctuation like this. When time constant was 1 second, I will have very slow fluctuation. When the time constant was 3 seconds, I will get a fluctuation like this, because I have only single data. This way you can see the fluctuation is minimized by increasing the time constant over which the data can be averaged. An example of this can be seen here. Here the velocity is 60 feet per minute and the time constant is 1, 2, 4 and 6. These are the beds, sand beds you can see here, where we have low, and these are the cell bed where we have high gamma ray log reading. So for high gamma ray log reading, generally it is not a problem, because let's say against silly formation we know that the gamma ray log reading is around, let's say, 150 API. So when a fluctuation of 4 to 10 will not result in the well logging engineer missing those bed. But in case of formation where we have low gamma ray count, it will affect our log data. So you can see how log response changes when I increase the time constant of 1 to 6. If I take it to high time constant, I am also missing a number of bed. A time constant of 2, I am getting very smoother response where the fluctuation in the log responses are eliminated. Even a time constant of 4, I am getting log responses where some of the beds are not properly characterized. So time constant may not be too low and it should not be also too high. So the equation time constant multiplied by velocity should be equal to 1. So the equation time constant multiplied by velocity equal to 1, this is observed on the basis of field experiences. So a number of log records have been analyzed, and it has been observed that when the multiplication of these two quantities equal to 1, we can get best log data. Another example you can see, time constant is now constant, that is 1 second, and logging speed is varying from 50 feet per minute to 120 feet per minute. At 15 feet per minute, you can see some variation. The curve is not smooth. The moment I am increasing the speed, you can see the fluctuations are removed, and a best record you can see, we can find that, you can see in this figure, in 30 feet per minute or 60 feet per minute, our log responses are much closer to the true natural radioactivity from the formation. When the velocity is too high, we are over simplifying the curve and some peak may be reduced. So time constant multiplied by velocity should be equal to 1 in order to get a best record from the our formation. Now let us discuss how to calculate the saliness of the formation or the cell content from the gamma ray log. Before we discuss how gamma ray logging can be used to calculate the cell content, let us first discuss, do we need to calculate the cell volume or clay volume from the well logs. We have already discussed what is the difference between shell and clay. Shell is made of clay, but it is not entirely clay. Shell generally contains 60 to 70% clay and rest is different types of mineral. So, do we need to calculate cell volume or do we need to calculate clay volume? So, the answer here lies that what is our objective? Our objective is to calculate either cell volume or clay volume to help us in the interpretation of different log data, particularly the data of our density log and the neutron logging tool. So we must consider how the response of density logging tool or neutron logging tool is affected by the presence of cell or clay. For example, we will discuss later on, the neutron logging tool is sensitive to the hydrogen content of the formation. So, if the formation have more hydrogen content, neutron log generally reads high porosity. If the formation have low hydrogen content, neutron log is going to read low porosity. And we know that the clay contain bond water and also hydrogen as a part of its chemical structure. So hydrogen is present inside the clay in the bond water and also as a part of its chemical structure. But this hydrogen is not related to any mobile water. So whatever the hydrogen is there in the bond water or as a part of the chemical structure of the clay is not mobile. So this hydrogen should not be taken as indication of mobile water or the pore spaces occupied by the mobile water molecules. So if I run a neutron log in rock which contain clay, it will think that I am getting a large hydrogen content, but this hydrogen content is not mobile. It is not associated with the mobile water. But neutron log does not know that. He will think that I am getting a good hydrogen content. That means there is large amount of mobile water may be there. So it is going to read this as extra pore spaces and will read high porosity. So if we must know the true porosity from neutron log data, we must know that how much clay is there because the hydrogen comes from the clay. So if I calculate cell volume, I am not actually detecting the hydrogen content in a true manner because the hydrogen is only inside the clay. I may be able to estimate the how much hydrogen is there if I know the clay volume. So the clay volume must be calculated, not the shell volume, because the hydrogen associated with the clay, the bond water is inside the clay, and shell only contains clay 60 to 70% by volume, rest is some other mineral. So generally clay volume should be calculated, not the shell volume, as the clay volume here it seems to be causing the most of the problem when taking the record of density log or the neutron log. But the problem with the clay content is that the clay volume cannot be generally estimated in an easy way. Generally, we can calculate the cell volume or the clay volume only if a bed of pure clay or pure shell is available, so that we can compare the log responses in a bed where, let's say for example, if I want to calculate cell volume, if I have a pure shell bed, I will compare the response of pure shell bed against a reservoir rock which contain certain amount of shell. So by comparing these two responses in a pure shell and in a formation which contain only certain amount of shell, I will get the saliness of the formation where we have certain amount of shell. So in order to calculate these two volumes, I must have a pure clay bed or pure shell beds. But generally pure clay beds are not common. So a clay bed which is entirely made of clay is generally not common, which is associated with our petroleum, which means hydrocarbon bearing rocks, which also contain the same type of clay we cannot find. Generally, we never have deposit of pure clay beds in our oil and gas bearing formations. So we cannot ascertain the response of pure clay. Whereas in shelly formation, pure shell bed or pure clay stone beds are generally common. We can find a shell rock or a clay stone rock along with our oil and gas bearing reservoir rock formation in most of the wellbore. So the calculation of pure shell response, let us say in the gamma log, is very easy because we have a pure shelly formation. So this response in pure shell bed can be used to calculate the cell volume. So the presence of a pure shell bed makes the cell volume calculation very easy. We have also discussed that many times we can use the cell volume and the clay volume interchangeably. Nonetheless, nowadays there are logs are available which can also calculate the cell volume and the clay volume easily from the logs. But many of the old logging tool or the combination of old logging tool, when using the most of the widely used petrophysical model, they generally going to give us the cell volume only. But we can also use the cell volume as a representative of the clay volume. As we discussed earlier, the clay can also be present inside our sandstone in terms of cementing material as a form of dispersed clay. So overall, cell volume may be equal to the clay volume. The total clay volume coming from the shell and coming from the other sources may be equal to our shell volume. So this way, sometimes cell volumes you will see in many logging softwares in our petrophysical model, cell volume may be directly taken as the clay volume. So V shell is often may be reported as V clay. So cell volume can be calculated by using a single log or a combination of log. These are the some of the methods which are available to the logging engineer to calculate the cell volume, such as core data or the SP log data or the gamma ray log data or the density neutron cross plot, sonic neutron cross plot or the sonic density cross plot. Today we'll discuss the gamma ray log, how to use a gamma ray log to calculate the cell volume. So we can calculate the cell volume just by using gamma ray log. One of the objective of calculating the cell volume is to help us in interpretation of our neutron and density log data. Also, on the basis of cell volume, we can define whether a reservoir rock is there or not. For example, we can define a cutoff value of cell volume. If the cell volume or cell content of the rock formation is greater than the threshold, that means it's not a reservoir rock. If it may contain fluid but not in sufficient amount with good property and permeability so that it can flow. So only the rock which have cell content less than the threshold value of the cell content can be described as the reservoir rock where sufficient amount of hydrocarbon would exist which could be produced. So threshold values could be defined on the basis of the logging engineer or the geologist expertise and depending upon the formation rock and fluid properties. So these are the steps that we need to follow if we want to calculate the cell content or the salines of the formation from the gamma ray log. So we can simply linearly extrapolate to get the cell content. That means what we can consider is that the gamma ray log response will increase with respect to the increase in the cell content. So from going from a sandstone or a clean sand bed or a clean carbonate bed or a clean reservoir rock, if we move to the pure shelly section, that means from 0% cell to 100% cell, our gamma ray count will increase in a linear way. It will going to increase in a linear way. So this linear extrapolation can be performed. So what we need to do is that first I need to define a shell line, that is the line going through against the formation which is made of purely shell, where the gamma ray log reading will be very high. Then I need to pick a clean sand or reservoir rock line. That means where I can say that the formation is pure or it does not have any shell. So generally on the basis of the core data You can see, or the rock cutting, you can see whether we have, if you analyze for the mineralogy, you can find out HV depth, we have pure section. This would correspond to the log responses where the gamma ray count is very very low. Those will be your clean section. So you can draw a line across the sand, clean sand, that will be your clean sand response. So from sand line you will get the gamma ray clean, that is the gamma ray log response, again clean formation. From shale line you will get what? Gamma ray log against a shelly formation. At any other place where the formation is made of both reservoir rock such as sandstone or carbonate and the shell is present inside the reservoir rock, you can calculate shell content nothing but what is the gamma ray log response in that section. Obviously that will be greater than the our gamma ray log against the clean formation. In a shelly formation the response will be more than the clean formation. So cell content or cellness can be defined gamma ray log minus gamma ray log clean divided by the gamma ray log response against shelly formation, gr shell minus gr clean. So a linear extrapolation here used to define the cell contents on volume basis or shelliness of the formation. For example, in this synthetic log, you can see this is gamma ray sand is 35, gamma ray shell is 135, and at this point I want to determine the our shelliness. So at this point, what is gamma ray log is 90. So the shelliness of VSH is 90 minus 35 divided by 135 minus 35, or it is coming around 55%. Now in early example I have taken the linear scaling, but many times the linear scaling may not be accurate. It may lead to overestimation of shell content. So depending upon the type of shell, a different correlations can be used. Different authors have given different types of correlation which can be used for different type of shelly rock, which are based on the gamma ray index. Gamma ray index is nothing but the our IGR, nothing but the earlier linear scaling formula. So IGR is defined as the GR log minus GR clean divided by the GR shell minus GR clean. This is nothing but the our earlier formula where we are using the linear scaling, and based on the IGR, like these are the different correlation which can be used for different type of shelly formation. For older rock, for tertiary rocks, this one is given by Clavier. So we can use any of these correlations to calculate the our shelliness depending upon the type of shell inside our wellbore in different depth. The choice of correlation could be used based on the logging engineer expertise, or we can take the help of the core data, and we can take the help of other method also such as density neutron cross plot. We can try to find a best match against known formation to get the best correlation suited for our particular wellbore where we are trying to calculate shell volume. You can see these equation if repeated in terms of graph at the same gamma ray index, you can see I am getting different shell volume. Linear scaling is giving me around 0.5 at 0.5 gamma ray index. If I use this equation, this is giving me around 0.3. If I use line off, it will give me around 0.2. So the data must be matched with the known data, or we can take the help of other log to get a good correlation to interpret the gamma ray log data to calculate the shell volume. Today we discussed about different factors affecting the gamma ray log response. Also we discussed how to use a gamma ray log to calculate the shell volume or shelliness of the formation. In next class we'll discuss about gamma ray spectrometry logging, and also we'll start discussion on density porosity logging.